Welcome to today's video. In today's video, we will be exploring the world of quantum mechanics, more specifically the quantum mechanical model of the atom, and the orbital theory and electron configurations. The quantum mechanical model of the atom represents one of the most profound advancements in our understanding of the atomic structure. This model, born from the principles of quantum mechanics, provides a more accurate and nuanced picture of the behavior of electrons within an atom than its predecessors. Unlike earlier models which depicted electrons as particles orbiting the nucleus in defined paths, the quantum mechanical model describes electrons in terms of probabilities existing within regions of space known as orbitals. The journey toward the quantum mechanical model began in the early 20th century, when classical physics was increasingly unable to explain this certain atomic phenomenon. The Bohr model, which depicted electrons as particles traveling in fixed orbits around the nucleus, was an important step forward, but it had limitations. It could accurately describe the behavior of electrons in hydrogen atoms but failed to account for the complexities of heavier elements and did not align with experimental observations regarding spectral lines. In response to these challenges, quantum mechanics emerged, a theory that fundamentally altered our conception of particles and waves. At the heart of this new approach was the realization that particles, including electrons, exhibit both particle-like and wave-like properties, a concept known as wave-particle duality. This duality was first proposed by Louis de Broglie, who suggested that particles could be described by wave functions. The wave function is a mathematical expression that contains all the information about a particle's state and can be used to calculate the probability of finding a particle in a particular region of space. Erwin Schrödinger further developed this idea by formulating the Schrödinger equation, which describes how the wave function of a system evolves over time. The solutions to the Schrödinger equation, known as the wave functions or orbitals, are not physical paths but rather mathematical functions that describe regions of space where an electron is likely to be found. These orbitals represent the quantum mechanical model's core concepts that are crucial for understanding atomic structure and electron configurations. In the quantum mechanical model, orbitals are defined by three quantum numbers: the principal quantum number, the angular momentum quantum number, and the magnetic quantum number. These quantum numbers correspond to the size, shape, and orientation of the orbital respectively. The principal quantum number determines the energy level of the orbital and its average distance from the nucleus. The angular momentum quantum number defines the shape of the orbital, with different shapes corresponding to different types of orbitals, such as S, P, D, and F orbitals. The magnetic quantum number specifies the orientation of the orbital in space. An additional quantum number, the spin quantum number, was introduced to account for the intrinsic angular momentum or spin of the electron. This property of electrons was discovered through experiments that revealed the presence of a magnetic field associated with electrons, suggesting that they possess an intrinsic form of angular momentum. The spin quantum number can take one of two possible values, often referred to as spin up or spin down. The Pauli exclusion principle, a fundamental principle in quantum mechanics, states that no two electrons in an atom can have the same set of four quantum numbers, ensuring that each electron occupies a unique state within an atom. The concept of orbitals and quantum numbers form the basics for understanding electron configurations, which describe the arrangement of electrons in an atom. The distribution of electrons among various orbitals is governed by several principles, including the Aufbau principle, Hund's rule, and the Pauli exclusion principle. According to the Aufbau principle, electrons occupy the lowest energy orbitals available, filling orbitals in a specific order as the atomic number increases. This principle explains why electrons fills the 1's orbital before the 2's orbital, and so on. Hund's law states that when electrons occupy the orbitals of the same energy, degenerate orbitals, they will fill each orbital silently before pairing up. This behavior minimizes electron-to-electron repulsions within an atom, leading to a more stable configuration. Hund's law explains the arrangement of electrons in p, d, and f orbitals, where multiple orbitals of the same type exist at the same energy level. The polar exclusion principle, as mentioned earlier, ensures that each electron in the atom has a unique set of quantum numbers. This principle is crucial for understanding the electronic structure of atoms and the formation of the periodic table. The periodic table in the properties of elements arises from recurring patterns in electron configurations as electrons are added to orbitals according to these principles. The quantum mechanical model also explains the observed periodic trends in the chemical and the physical properties of elements. As electrons are added to the orbitals across a period, the effective nuclear charge experienced by the electrons increases, leading to a decrease in atomic radius and an increase in ionization energy. Conversely, as electrons are added to higher principal energy levels down a group, the atomic radius increases and ionization energy decreases due to the greater distance of the valence electrons from the nucleus and increased shielding effect of inner electrons. The quantum mechanical model has also provided deep insights into the nature of chemical bonding. The overlap of atomic orbitals and the formation of molecular orbitals, as described in molecular orbital theory, is a direct consequence of the quantum mechanical description of electrons. This theory explains the bonding of molecules in terms of the constructive and destructive interference of electron wave functions, leading to the formation of bonding and anti-bonding molecular orbitals. The concept of hybridization, which describes the mixing of atomic orbitals to form new equivalent hybrid orbitals, also arises from the quantum mechanical model. Furthermore, the quantum mechanical model underpins our understanding of complex phenomena such as electron correlation, the behavior of electrons in multi-electron atoms, and the limitations of the Hartree-Fock approximation. The development of a more advanced computational method, such as density functional theory, DFT, which allows for the calculation of electronic structures in molecules and solids, has its roots in the quantum mechanical description of atoms. The implications of the quantum mechanical model extends beyond the confines of atomic structure. It has revolutionized fields such as chemistry, material science, and nanotechnology, enabling the design of new materials and tailored electronic properties. The principles of quantum mechanics have also laid the foundation for emerging technologies such as quantum computing, which promises to harness the strange behavior of quantum particles to perform computations far beyond the capabilities of classical computers. In summary, the quantum mechanical model of the atom represents a monumental leap forward in our understanding of the microscopic world. By describing electrons in terms of probabilities and wave functions, this model has provided a more accurate and comprehensive picture of the atomic structure, explaining the behavior of electrons in atoms, the formation of the periodic table, and the nature of chemical bonding. That wraps up for today's video, and thank you everyone for watching, and thank you for your patience and time. See you in the next video.